Okay, here we go. All right. What's up, everyone? So we've talked a bit about this correspondence that you see on the screen right here, where we're looking at spans of some subsets of Rn as well as subspaces of Rn. And last time I claimed that they were actually just the same thing. Now, so I talked on like during office hours or during Discord with a few people, and they told me that they were confused about like what span meant or what all this means and all of that. So I thought I'd clear some things up, and then we're going to show this side of the correspondence so that if you have a span of a certain number of vectors, then actually that's a subspace of Rn. And then in a future like video or recording or whatever, we'll do the opposite way. Okay, so first, the question everybody's been asking me, what is span S given S a subset of the real numbers? Okay, well, what does that even mean, right? So let's do an example because that's confusing. So let n equal 3. So we study R3. Okay, here's the most boring example I've ever seen in my entire life, but this is the one that books always give. So the span and we're gonna write it like this because we've been doing things like this. 0, 1, 0. So example 0, 0, 1. This is R3, and then they don't really explain why, right? And they say, oh, well, if you take all linear combinations of 1, 0, 0, B 0, 1, 0, and C 0, 0, 1, then this is equal to ABC for some A, B, C, and R, and so that must be everything. Okay, well that doesn't really tell you anything, right? We're still confused. We don't know much. Okay, so forget this. Scribble it out in pink. Let's think about it this way. The span of let's say what do I want to call them? Let's call them V1 up until Vk, where k is your favorite number. And don't worry, I will do an actual example in a bit. But the span of Vk, V1 up until Vk is all the possible ways. Here, let's put it in red. All the possible ways you can multiply a number to each of the V's and add them up. So an example of this, let's say k is 5. So we're looking at a list V1, V2, V3, V4, and V5, right? I want to look at all the different ways I can multiply a number and add them up, right? So let's call a span of this set. Let's call this thing U, right? So first of all, 0 is in U, right? 0 is in U because 0 is equal to 0 times V1 plus 0 times V2 plus 0 times V3 plus 0 times V4 plus 0 times V5. So anything, literally anything that you can just multiply a number in front of each one of those 5 things, add them together, that is in span of those things, right? Because that's precisely what it means for that thing to be in the span. Okay, next, V1 up until V5 are all in U. Well, they kind of have to be. This is one of those things because, like, for example, V1 is 1 times V1 plus 0 times V2 plus times V5. V2 is 0 V1 plus 1 V2, and okay, and so on. So each one of the things that it's like, each one of the things in this set that you're looking at the span of must be in the span of that set, right? Otherwise it wouldn't make any sense, right? So, and I'll show you what this means pictorially in a bit, but let's do a couple examples. random things like, I'm just going to pick my 5 favorite numbers, right? So pi v1 plus e v2 plus square root of 3v3 plus 9001 v4 minus, right, because we've got to put some minuses in there, 3 over 4 v5. This has to be in u, right? Because all I did was put my favorite numbers, multiply each of the v's by them. Well, that has to be in the span, right? So I hope now we see what span means a little better. And now let's look at what this means pictorially, right? So, so span of v1 for a single vector v. Here, let's erase the subscript 1. Okay, so let's look at the span of a single vector v, and what does that mean, right? So to write the definition, this is all the ways, all the things that are like a number times v, right? For some number a, right? So you take a vector and then, well, if I look at the span of that vector, it's all the scalar multiples of that vector. So this is all scalar multiples. And what that looks like pictorially is, here, let's see. Let me draw you a picture. So let's say we're in R2 now because it gets too hard to draw R3 too many times. So let's say here's the vector v, right? Okay, that's v by itself. Only this point right here, kind of. You can think about that in relation to 0. Okay, well, if I want to look at the span of it, I have to take every single possible scalar in all of R, multiply to v, and see what happens, right? So let's just start throwing random numbers down in there, and let's maybe, hopefully, this will get our intuition going. So if we know, let's see, we know 0 is in span of v because of what we set up here. 0 is always in there because 0 is in every subspace, but we don't know that it's a subspace yet. So that gets filled in. We know that v itself is in span of v, right? So that gets filled in. We know that 1/2 v is in span of v, right? Because, well, it's a number, right? What's another number? What about -2, right? This has to be in span of v. So 1, 2, well, minus v has to be in there as well. Okay, and then literally any number I put, right? So here's -1/4, here's 1/4, here's like pi, here's 2. Oh, geez, it's not. Okay, now all the numbers between 0 and 1 have to work. All the numbers between 1 and 2 have to work. Whoops. And if you think about it hard enough, any number, as long as it's in the same direction of v, has to work, right? So pictorially, what that looks like is we conclude that the span of a vector, of a single vector, v, is the line pointing in that direction. Line pointing in that direction. Okay, we talked a little bit about that last time. So the natural upgrade to that, it would be to consider the span of 2 vectors, right? So how about the span of 2 vectors? About span of 2 vectors, v1 and v2. Okay, well, let's do the same exercise. So, okay, let's draw 3D space. And for my convenience, we are going to make them pretty easy to draw lines. Okay, let me think about which point I want. Okay, so let's say this is v1, right? And let's say this is V2. Just picking a really easy example because you can always rotate the picture however you like. Okay, based on the last example, well, if V1's in there, so let U equal span V1, V2. Okay, if V1 is in there, then so is that whole line that points in the V1 direction, right? So all this gets filled in, all this gets filled in, and so on in both directions, right? If V2 is in there, then so is everything in its direction, both up and down, right? Okay, so we've covered all like A times V1 and all A times V2, right? Or let's put A prime or something. But what about things that look like V1 plus V2 or like 5V1 plus 6V2 or like those things where both of them get numbers and not just one of the vectors shows up? Well, let's look at it. Okay, so what is V1 plus V2, right? Because that has to be in the that has to be in the span of V1 V2 because it's a number times V1 plus a number times V2. Well, that particular one looks like this. Here, let's make it a little thicker. So there's V1 plus V2, right? Well, I can also have like 2V1 plus V2. This has to be in U. Both of these have to be in U. That one doesn't look like that. I lied. That one looks like this, right? So that's in there. And then, well, you can kind of guess what happens, right? But I want you to draw a couple more of these on your own. Here, I'll do a few more for you. So V1 minus 2V2 looks like this. But the key thing to note is that they all lie on this same plane. They all lie on this plane that contains, right? Because two vectors determines a plane, unless they're collinear, and then you cry, but they're not. So this plane, and I'll try my best to draw this. So this plane is the span of V1 and V2. As long as V1 and V2 are not collinear. So what does this tell us? The span of one vector is a line. The span of two vectors is a plane. So we expect the span of three vectors, so long as none of them are like, well, so long as the third one doesn't lie in the plane generated by the first two, to be 3D space, right? So this generalizes to however many vectors you have. Okay, let's see. So span of V, let's just make it easy to look at. This is the same thing as a line. Span of V1, V2. And then I have to put V1, V2 not collinear. This is a plane. The span of V1, V2, V3. And I'm going to put V1, V2, V3 not coplanar, right? Because that's not a very interesting case. That's the same as a 3D space and so on, right? Okay, so now we know roughly what spans look like. Maybe this concept is still a little confusing, so let's do a specific example. So let's study span of, and I'm just going to put two random vectors that I like, right? I'm going to put 1, 0, 1, and I'm going to put 0, 1, 1, right? I tend to use this example a lot, it seems. Okay. So let's draw this because we can actually draw this. X, Y, Z. So 1, 0, 1 looks something like Okay, let's see. 1, 1, 1. And so 1 in the x direction, 1 in the z direction looks something like this, with the shadow on the x-axis. And 0, 1, 1 looks something like this. And so in the first octant, the image we see is we see this kind of plane between them, right? Okay. So let's study that. Okay, so that's what we expect. Let's just write out a couple example elements, right? Example vectors in, let's call this thing U, in U. So I could take one of each, 1, 0, 1, plus 1 times 0, 1, 1, right? I can put any numbers I want right here. So I'm putting 1 in each. And if you add them together, you get 1, 1, 2, right? Okay, what does 1, 1, 2 look like? Well, 1, 1, 2, if I continue this plane, is up, let's see, so we trace the square. And so then we go all the way up until we hit the thing. And that looks like it's twice as high up as this point is, right? So 1, 1, 2 is indeed on that plane. Let's try another one. Let's try 1/2, 1, 0, 1, plus a 4th, 0, 1, 1, right? That's allowed because those are two random numbers that I multiplied to the vectors. So therefore it has to be in the span of them because, you know, that's how this stuff works. So let's see what we get. We get 1/2, 0, we get a 4th. And for the third entry, oh geez, we get 3/4. So where that is on here, let's see, 1/2, 1/4 is about there. And then I go up right there, this point on that plane. Okay, try to visualize it. You can do it, I believe in you. Okay, so let's look at a point not in the span, right? It looks like the point, 1, 1, 0. Or here, let's write it in the notation we've been using. It looks to me, or apparently this picture would suggest that the point 1, 1, 0 looks like it is not in the span of 1, 0, 1 and 1, 1, 0, right? Or 0, 1, 1, sorry. Okay, well, let's show that, right? So let's say I have two numbers, A times 1, 0, 1 plus B times 0, 1, 1 equaling your mystery vector, right? 1, 1, 0. So suppose this. So the key thing for me is I want to find A and B that do exactly this thing that we've said here, right? I want A and B where I multiply the first vector and the second vector by A and B respectively. I add them up. I'm supposed to get this vector. That's what you're telling me. But I'm telling you this is impossible because that point is not on the plane that I drew, right? This point is not on this purple plane up here. Okay, let's show that, right? So if this were true, let's simplify this expression, right? What do we get? Well, I get an A in the first entry because if you go like this, you get A, right? If you go like this, you get B, so B is the second entry. And if you go like this, you get A plus B. Okay, so that's supposed to equal 1, 1, 0, right? So now I just match the entries up. So A has to equal 1, B has to equal 1, and A plus B has to equal 0. Well, if that were true, that would mean that 2 equals 0, which is impossible. Impossible. And so that's why you can't do that. Yeah, okay. If you remember from last time, if you watched the video before this one, then it would look something, you would do something like this. Let's see, 1, 0, 1, 0, 1, 1. And then you would notice, let's see, 1, 1, 0. You would notice that this was actually impossible, right? you would realize you would try to solve this, right? Because then you would put this like into this this thing we set up last time. And then once I row reduce the first two rows, you're going to find this happen. Or sorry, the first two columns. It turns into this. 0, 0, 1, 1, 1, 0, 0, minus 2, right? And if you have a row of zeros in the beginning and then a minus 2 at the end, that shows you it's impossible. So everything is working exactly the way it's supposed to. Okay. So now let's show that this thing actually is a subspace, right? So I'm going to do it for just an arbitrary number of vectors, and then I want you to specialize it for whatever problem that you're doing. So if S is a collection of vectors, which is contained in some vector space, then span of, here, let's just write it out, is a subspace of Rn. So if you remember our template from last time, what is the first thing we should do, right? So the first thing I should do is I should show that 0 is in my subspace. So I'm going to annotate in green. First, show the 0 vector is in, let's call this thing U. So let U equal span of, yeah, no, this is redundant, get over it. Okay, so we've got U is the span of all this stuff. Then the 0 vector is equal to 0 times V1 plus 0 times V2 all the way up until 0 times Vk. So that must be in U because this must be in the span because it's a number times V1 plus a number times V2 plus a number times V3 all the way up until K, right? Okay, so we got the 0 part down. The next thing we want to do is here, I'll just write it. Let's write this in green. Let V1, oh no, I don't want to use V1. Okay, here, we have to use different letters, darn it. U1 and U2 be in U and C be a real number. Any real number, your favorite real number, who cares? And then I have to show that U1 plus C times U2 is contained in U, right? That's the goal here. Okay. So remember, the next step after saying U1 and U2 are in U is to unpack what that means. So what does this mean, right? What does this mean? Okay, well, to be in U means you're in the span of V1 up until Vk. To be in the span of V1 up until Vk means you're just a thing, which is a bunch of numbers times V1 up until Vk added together, right? So I can say U1 is, and I picked my favorite numbers in the world. It doesn't matter what they are. A1, let's call it A1. That's my favorite number in the world. V1 plus A2, V2 up until AK, Vk, right? Where I pick the A's in such a way that I get U. So for some, and people will write it like this, A1 up until AK, that is an element of R, so those are real numbers. The TLDR for this, A1 up until AK are real. That's all that means, they're not fake. Okay, so because to be in the span means I can find you these numbers, right? These numbers exist by virtue of U1 being in the span, right? So I could say the same thing for U2. U2 is in the span of V1 up until Vk. That means these mystery numbers, I'm going to call these ones B1 up until Vk, B2 up until Vk for some B1, Vk in R. So in other words, U2 in U is the same as saying, Oh, I shouldn't put the implication there. U2 and 2 is U2 is in U is the same as saying there are numbers B1 up until BK so that this happens, right? So we have that U1 is all the V's times a number added up. U2 is all the V's times a bunch of numbers added up. Okay, we want to show that U1 plus C times U2 is also all the V's times a bunch of numbers and then added up, right? So let's just do that. So then I messed up already. U1 plus C times U2. Okay, just like in the previous example, we're gonna take this and replace it with that, right? So I'm literally gonna copy paste that thing over there. AKVK plus C times, and then I'm literally gonna take this, right? And then I'm gonna copy paste it with that. So B1, V1 up until BK, VK, right? So this got replaced with what was on the other side of this equal sign, and this got replaced with what was on the other side of that equal sign. So that equals, well, I can kind of rearrange everything, right? So here, that's A1, V1. So that's this guy, and then I'm gonna move this guy over. So plus CB1V1 plus A2V2 plus CB2V2, and so on, until I get to the very last thing, AKVK plus C times BKVK. Let's see, CBKVK. Okay, now you'll notice the first, I can group them up like this. And in this first group, these all have V1, these all have V2, these all have VK, and everything in the middle. So I can factor those out. A1 plus CB1 times V1 plus A2 plus CB2 times V2, and so on. AK plus CBK times VK. Okay, what have I done? What have I done? Now, everything in here is a number. So the whole thing is a number. Thing is a number. Now this is a number. That is a number. And everything in the middle was a number, right? So what have I done? I have said U1 plus CU2 is a big sum of numbers times V1 times V2 up until VK, and then you just add them all together, right? So what this says is, this means that U1 plus C times U2 is an element of U, which means that U is a subspace of Rn. Now, notice. I maybe don't actually need this fact right here, right? I maybe don't actually need that fact because I only used it at the very end, right? In fact, this argument works for span of like abstract vector spaces in general, but I don't want you to worry about what those are quite yet because you might get very confused, which is completely fine. Okay, so let's recap real quick. We were studying the idea of span of some set is the same as a subspace, right? So first, we gave the book examples, which I claimed were really bad. And then we rephrased the span as all the possible ways you can take everything on that list, multiply a number, and then add them all up, right? Now, if you think long and hard enough, isn't that just a really cheap way of saying, hey, I want to make a thing where it's a vector space, but it contains this list that I gave you, right? And that's exactly what you've done. Exactly what you've done here is that idea span of V1 up until VK is the smallest, quote unquote, I'm going to put this in quotes, vector space containing v1 up until vk. Because what you've done when you add all those things together, you're saying, hey, I'm going to force this thing to be closed under addition. When you add all the numbers, you're saying, hey, I'm forcing it to be closed under scalar multiplication. So essentially what you've done is you've forced this set v1 up until vk to also be a vector space, just kind of by design. But anyway, we're getting kind of off topic here. So we did some examples. We showed u is always in the span, which makes sense because zero is always in the span, which makes sense because 0 is always in your vector space. We showed the original things had to be in the span as well. And then finally, we just, instead of looking at these really abstract examples, we wrote some concrete ones down, like pi v1 plus ev2 plus all these silly numbers. We showed that the span of a single vector is a line. If you take 2 vectors, you get a plane. And if you take 3 vectors, you get a 3D space. And if you get 4 vectors, you get a hypersurface and so on. Okay. Well, here's another bonus. Here I said v1 and v2 had to be not collinear. v1, v2, v3 had to be not coplanar, and so on. You can nicely summarize all these things as saying v1 up until vk are linearly independent. So yeah, I'll talk more about that next time, but yeah, okay. We looked at the span of 2 vectors, we studied the plane, we showed if you're outside the plane, then you're actually not a linear combination. And then finally, we showed that the span of k vectors is a subspace of Rn. And then, yeah. So that concludes if you're a span of something, then you're a subspace, right? And so the next step would be, if you're a subspace, then you're actually the span of something. But that's kind of hard and relies heavily on linear independence. And then it's like, well, the argument goes something like this. Basically, because you show Rn's finite, right? Rn can be generated by n different vectors, and that any choice of n linearly independent vectors must give you Rn. Okay, so first you show that. Then the second thing you do is you say, okay, well, if you have a subspace, just start picking vectors and closing them under span until you can't do that anymore. Well, at some point you have to stop, otherwise you get all of Rn, and then yeah. So we'll do that next time. I hope you learned something today, and I'm gonna peace out now, bye.